Welcome back to Chem 4300. In this video, we're going to continue Chapter 10 on wave-particle duality, and now we're going to focus on the photoelectric effect. This was a very important piece of experimental evidence that was used in the development of quantum theory. So this idea, or this effect, was discovered by Heinrich Hertz in 1887. Let's take a look at the apparatus that he had set up here. So what he had was a vacuum chamber. So this area inside this region here is all evacuated, so there's no air. And in this vacuum chamber, he placed a cathode and an anode that were connected in a circuit, but there was now a gap between them. And in this circuit, he placed a voltage source so he could bias the cathode and anode relative to each other. And there was also a current meter so he could measure the current flow in this. So in this apparatus, if you bias the voltage on the anode so that it's positive relative to the cathode, you can eventually reach a voltage where electrons will be pulled from the cathode and attracted to the anode. And once they hit the anode, then you have a current that's flowing in your meter. Now, what Heinrich Hertz discovered is that if you shined light onto the cathode, you could increase the current that's flowing in this apparatus. So in this setup, then, he also had a quartz window on one side of the vacuum. He had a hole in the anode, and the light would shine in on the cathode, and with the light shining, the current would go up for a given voltage here. So just to show you, without any light, you had some current flowing, but with a given voltage, you turn on the light, and the current goes up for the same voltage. So this was called the photoelectric effect. And at the time, actually, the electron wasn't even discovered, so it wasn't quite clear what was going on to what was the charge that was moving across. But in 1887, J.J. Thomson discovered the electron, and at that time, scientists went back and looked at this photoelectric effect and with a little bit more detail, looking at things like what happens when you vary the light intensity, what happens when you vary the light frequency. And let's look at what the results were. So we know that as you increase the voltage, that eventually you reach some voltage where you can pull the electrons off the cathode and make them hit the anode. And if you keep increasing the voltage, you'll pull more and more electrons off of this cathode, and eventually you reach some limiting current where the current now becomes stable no matter how much higher that you increase the voltage. So the story then is that we're going to systematically vary these guys, and we're going to measure the current that flows as we vary voltage, light intensity, and light frequency. All right. So if you vary the voltage, so this potential here is just adjusting this guy, increasing it. So you can see here that the behavior where it goes up and then it comes to some limiting value. And now if you increase the light intensity that's shining on a cathode, you see just doubling the light intensity will double the current that you see in this apparatus. Now, the interesting thing is that if you bias the voltage the other way so that the cathode is negative, the anode is negative relative to the cathode, then you can start slowing down the electrons. So if I go back to the previous slide, you can see that if I made the anode negative relative to the cathode, then the ejected electrons, which are coming off due to the fact that there's light shining on them, the ejected electrons will be slowed down because now they're approaching a negatively charged anode. And as this anode becomes more and more negatively charged, then the repulsive force acting on the electrons as they're coming towards them will get greater and greater. Eventually, you can make this even more negative, so eventually you can stop the electrons from hitting the anode. And that's what's done here. So if you bias on the other side, so if you go the other way, you start seeing the current going down, and eventually you reach a particular voltage where you've stopped the electrons of the fastest electrons that are coming off this cathode. So this voltage we'll call phi naught is the voltage that's needed to stop the fastest electrons. And if we multiply that times the fundamental charge, then that's the kinetic energy of those fastest electrons. Now, classical wave theory says that light energy is related to the light intensity. The bigger the wave, then the more energy the light has. The smaller the wave, the less energy the light has. So you would expect that if you increase the light intensity, then you would put more energy into the electrons and you would need more negative voltage to stop the electrons, right? But you see that if I double the light intensity, I still need exactly the same negative voltage to stop the electrons. And that didn't quite make sense. I increase the size of the wave, I should need more negative voltage as I increase the intensity of the light. But no matter what intensity of the light I have, they always stop at some negative bias that's exactly the same, regardless of intensity. So that was kind of confusing. But in these systematic investigations, what they found was that if they varied the light frequency, so again, go back to the apparatus, so that was just varying light intensity. But now if you hold the intensity constant and you vary the light frequency, what you find is that the stopping voltage that you need becomes linearly dependent upon the light frequency. So as you make the frequency higher and higher, you need greater and greater stopping voltage. So, or more negative stopping voltage to make the electrons not hit the cathode. So here you see what you get. This is the slope of the line, and it actually depends upon the metals that are in the cathode. So for rubidium, potassium, sodium, these are what these curves look like. And so there are particular frequencies where if you go below those frequencies, then the stopping voltage goes to zero. So this quantity then, this frequency, this critical frequency below which no electrons are emitted, is what's called the work function of the metal. So once you exceed this critical frequency, then you start liberating electrons from the metal. But if below that frequency, the electrons are not liberated by the light shining on them. So this varies from metal to metal, and this is the energy of the light going into releasing the electrons from the metal, and with the remaining energy going into the kinetic energy of the electron. So there's a certain threshold energy that's needed to pull the electron out of the metal, and then whatever's left over in that energy goes into the kinetic energy of the electron. But now, of course, as we saw, based on classical wave theory, where it's the amplitude of the wave that determines how much energy the wave has, now we're seeing that somehow the frequency of the wave is determining how much energy is in the system. And this was not making sense according to classical wave theory. And so the solution, or the simple explanation for this, came from Albert Einstein. So this was 1905. Einstein, looking at these results, said, one way we can nicely interpret these results is that the light is actually composed of bundles of energy. He didn't call them photons, though it was a name developed later by G.N. Lewis. But he said if these bundles of energy, which I'm going to call photon, came in bundles that are proportional to the frequency, where h is Planck's constant, then this could explain the result, that the energy was related to frequency, obviously, because that was the only thing that changed the kinetic energy of the electrons, not the amplitude. And so we see that this simple interpretation is what he found gave a good explanation for it. And actually, he got the Nobel Prize for this in 1921. And let's take a look at more detailed analysis that he did based on this understanding. So at the time, remember, 1905 was a killer year for Einstein. He also published his special theory of relativity. So he knew that if light was a particle, and it was a particle moving at the speed of light, he could use his special relativity to try to understand what its energy was and its momentum, assuming it was some particle. Now, he knew from just sort of regular particles that were moving closer to the speed of light that the energy was given by this expression and the momentum was given by this expression here, where this is the mass of the particle, this is the speed of light, this is the velocity of the particle, and this is the momentum here. So these two equations, you can describe any particle, whether it's an electron or a bowling ball or a rocket ship. All of them will obey these relativistic equations according to special relativity. Now, for a photon, if a photon is a particle, then he would find, of course, he has to use the photon as moving at the speed of light. That's the speed at which photons move. So if you put that into this equation, then suddenly you have 1 minus 1, which is 0. So you're dividing by 0, and that gives you infinity for the energy of this particle and infinity for the momentum. So that's not good, right, if you're trying to use this approach. But he also looked at these equations and said, well, wait a minute, if the mass of the photon was 0, the rest mass was 0, then I would be dividing 0 by 0, which in that case, 0 divided by 0 is undefined. So that doesn't mean that it's infinity, it just means that now these are undefined. We need another way of solving this problem. So what he's going to do then is he's going to continue with this idea that the photon must have a 0 mass and look at another way to figure out what its momentum is. So we're going to take those two equations that we just had and we're going to rearrange them. So if you go back to the previous slide, take both sides and square them and then move the denominator over, move the numerator over, and we can rearrange this so that we get this expression and this expression here. All right? So now, with a little bit of algebra here, I can subtract this guy from this guy, which I get this expression, and you can check that this expression actually equals 1. Right? So we just have the same thing in the numerator and in the denominator. So that leaves us with this expression over here equal to 1, which I can rearrange to give me this. That tells me that the energy is related to this quantity and this quantity here. Now, if I take the square root, then I have this expression, and since the photon has a mass of 0, this term has to be 0, which means now I'm taking only the square root of this guy, which is squared, so that means that the energy of the photon is equal to its momentum times the speed of light. With Einstein's previous proposed energy for this wave, this light packet, this thing called the photon, we plug that equal to this guy, and we get this expression that the photon energy is equal to hc over lambda. So with that, then we find that we can remove the C naught, and we get that the photon's momentum is just Planck's constant divided by wavelength. So now Einstein proposed not only that the photon, the light comes in packets with this energy of h nu, but also that the momentum of this particle, this massless particle, is Planck's constant divided by the wavelength of light. Okay, so even though it's massless, it carries momentum, and it's related to the frequency or the wavelength of the light. Okay. Now, momentum is a vector quantity, and we know from classical E&M that the momentum vector is related to the wave number vector. So this is the unit vector along the wave number direction with times E over C naught, okay? And so E is the energy of the wave. So if I take Einstein's expression for energy and I plug it in here, then I can rewrite this expression so that now that the momentum vector is equal to h over 2 pi times the k vector here. Remember, this is just the unit vector along the direction of k, and this is 1 over lambda, so we can rearrange this with our definition of k over here, and we can write that the momentum vector is just proportional to the k vector times this proportionality constant h over 2 pi. And in fact, h over 2 pi, Planck's constant divided by 2 pi, is used so often that we define a new constant which is called the reduced Planck constant with an h with a little line through it, and that's always supposed to represent h over 2 pi. So the more condensed form of that is, that equation is that the photon momentum is just equal to h bar times the wave vector. Okay. Now, finally, we come to this sort of interpretation of what all this means. So Einstein was trying to understand then how to interpret this older wave theory picture that the wave intensity was related to the energy, to this new picture where the energy of the light was equal to h nu. And so he said, in old classical wave theory, we know that the intensity is going to be given by this expression. We learned this in the earlier chapter, and that is independent of frequency, of course. And in this new picture, the intensity is just going to be how many photons are hitting the electrode, right? So the photons in this case was just the average number of photons per unit time times h nu. And this is, of course, moving along the direction of the wave. So here we have two expressions. This is what you would have from classical wave theory, and here's what Einstein was proposing. So somehow we know this is true, we know this is true, so what's the interpretation here? And what Einstein suggested was that this quantity here, the electric field squared, average value electric field squared, is some kind of measure of the average number of photons per unit volume. So he took a sort of statistical view that the light intensity with these E field and B field waves as some kind of guiding wave for the photons, and the light intensity, the wave intensity, was gave you some kind of probabilistic interpretation in terms of it's the probability that a photon is emitted or absorbed. So in this interpretation, then it's not the wave that carries the energy, but the photons, and the wave determines the probability that that electron, or probability that photon is emitted or absorbed. And so this was Einstein's sort of full interpretation of the photoelectric effect. He proposed that the energy of the photon is this quantity h nu, and that the wave amplitude squared, the intensity of the wave, is something that you interpret in some kind of probabilistic way to give you the probability that a photon is absorbed or emitted. And so that's it for this video. And the next chapter we'll go from light to matter. So we now have Einstein's picture and Planck's picture of how light becomes quantized and how we can use this idea of light being associated with photons and this probability picture. Now we move on to how we describe what happens to, say, electrons and protons and other types of matter at the microscopic level.